Hi, I'm Kaye. I'm the Associate Director for Research in the Earth Science Division at NASA headquarters in Washington, D.C. What I'm going to be talking to you today is about studying atmospheric chemistry from aircraft. Title says chemistry at 30,000 feet, but of course, since it's from an aircraft, there's lots of altitudes that we can use. In doing this, I'm drawing on the work from a number of people, some of whose names you can see here. Well, I'm going to talk about aircraft. I wanted to start out, though, talking about satellites, since that's the biggest part of what we do in the Earth Science Division. We have a robust fleet of orbiting satellites that we use to study the Earth as an integrated system, covering the oceans, ice, land surface, biosphere, atmosphere, looking at all the different Earth system components and how they interact with each other, getting to a good approximation, equivalent quality data anywhere on the Earth, and using a variety of techniques and wavelengths and orbital geometries to get the information that we need. That kind of coverage is really unprecedented in terms of our being able to look at the whole Earth, but just the spatial resolution that one gets and limited vertical resolution or inability to see under certain circumstances, like under clouds, means that you can't necessarily get everything with the satellites. And especially if you really want localized information, they may not be the best way to do that. And being able to make that connection between the big picture, top-down global view of satellites and what's frequently the much narrower localized view that one wants to get for understanding processes, especially in things like ecology, is important, and the aircraft play a role in bridging between the two. This chart shows how one does that. You have the big picture, top-down view of the satellites, but then when you may get down to a specific plot, and the aircraft can, in some cases, focus as a virtual satellite, have a satellite like payload, but then you can target it just the way that you want to with the trajectory that you fly. But the aircraft can do a lot of other things, very comprehensive process information, localized in space and time, with a more comprehensive payload than you can get on a satellite, so therefore you can thoroughly interrogate the area right around the aircraft or above or below it. You can also use it as a calibration validation platform for testing what satellites do, and as a platform for technology development tests. And it's also a great place for hands-on activity from early career professionals. So the aircraft will serve to do all of those. At NASA, we have a fleet of aircraft ranging from a ER2. It's a modified U-2 spy plane with just the pilot on board. It goes up to 70,000 feet. We have a DC-8. It's the largest of the aircraft. It flies at up to 41,000 feet. It literally was a commercial aircraft. It's a narrow-body jet, but instead of 6 seats across, it's maybe 30 seats or so scattered throughout the plane, but otherwise filled with instruments, as well as holes in the side for inlets and upward and downward looking ports so that one can look above and below the aircraft. And there's a variety of aircraft in between, business jets, propeller planes, and smaller planes that we'll use. And we have a long inspired history at NASA of using aircraft for studying the Earth, with a combination of the aircraft, the instruments or sensors that we use, the systems that let us be productive, the people, and the opportunities. Speaking of opportunities, I'll next show you some of the kinds of things that we've done to study the Earth's atmospheric composition, and then give you some specifics about some recent things. This chart gives you a sense of what we've done over not quite the past 40 years for studying tropospheric chemistry from aircraft. You can see a lot in the Western Hemisphere, some in East Asia, some out over the oceans. It's really quite a bit. The abbreviations are the names of the campaigns. I'll say some things about the examples for that later on. We also have a similarly long history in looking at the stratosphere. So this shows it's closer to like 33, 34 years. So not as many campaigns that we've had. You see especially a lot at high latitudes because of some of the polar campaigns that we've done, but also things in the tropics and out over the oceans and over the continents. A variety of places that we've done. So it's really quite a bit. Next, I'll review some of the more recent history and some of the things that we have coming in the future, and then go to some details. So this chart lists some of the campaigns that we've done or are going to do, the dates, the locations geographically, but then the locations sort of vertically to say whether it's lower troposphere, where it tended to be focused on air quality, upper troposphere, where it might be focused on sort of global air quality and long-range transport, or climate forcing, lower stratosphere, upper troposphere. They could get at things like water vapor and its transport between the upper troposphere, lower stratosphere, or more in the middle stratosphere, where one looks at the chemistry of ozone. And you can see the platforms that are used. It's really quite a variety for these particular campaigns. Kaye DC has been, it's the largest platform. As I said, it literally was a commercial jet, 4 engines, narrow body. And it goes up to 41,000 feet, can fly for 12 hours, and cover about 5,400 nautical miles with a payload of 30,000 pounds. So it's a real workhorse. It can fly regular jet fuel and commercial airports. And you can see when the plane is loaded up with instruments, there's a lot of instruments, a lot of things sticking outside the windows with ports, as well as places to look up and look down. People working very, very hard during the flight, and a lot of sampling. It's a beautiful bird that can really do quite a bit, and that's going to be an important one for atmospheric chemistry because of the breadth of the comprehensiveness of the observations that it can do. So this is one example. When you load up the DC-8 with certain payloads, these are the compounds that can be observed now. That's not going to be what we do with every campaign, but those are all compounds that have been measured from the DC-8. And that kind of chemical comprehensiveness can be really important because when you're trying to build and test models, having a very expansive, comprehensive set of species, especially where you may be able to get source gases and reservoir species, maybe some free radicals, really let you test the models and make it so that when the models are so constrained, it's very hard to say get the right answer for the wrong reason. There's no better way to test models than to have a lot of information, observations that need to be matched. One of the campaigns that we did was the Discover AQ campaign. It was part of our Earth Venture suborbital campaign. We used multiple aircraft and did campaigns over a period of years. Started in the Baltimore, Washington area, went to the Central Valley of California, went to Houston, and then went to Colorado. And besides being able to underfly satellites and do vertical profiles and overfly ground stations, it's helped to serve as a nucleating phenomena to bring input and personnel and equipment from the local regions there, and especially to add to the ground-based component. So we were able to learn a lot about that, and with each successive campaign, even if they were in very different environments, learn from what we had done in the previous campaign. In 2016, working with partners in Korea, we did the Chorus AQ campaign with the DC-8 and the B-200, and Korea had aircraft and there were ships and surface-based measurements, and really trying to look at air quality over Korea, understanding what was locally generated, what was brought in from elsewhere by the winds. Korea's got a big economy, a lot of people, and it's a peninsula nation, so there's a lot of opportunities for having very complex chemistry. It also turns out that Korea now is the first country that has a geostationary air quality satellite. So the work that one did by being able to get vertical profiles of ozone and other constituents provided information to help anticipate and test algorithms that would be used by the GEM satellite that Korea launched recently. And looking ahead, there will be other geostationary air quality satellites, TEMPO in the US and Sentinel-4 from Europe. So the information that we get by looking at this will help us prepare for other geostationary air quality measurement satellites. More recently, in 2019, working with our partners at NOAA, we did the FireX-AQ campaign, had the DC-8 there, and NOAA had an aircraft as well, to look at the atmospheric impacts of fires, both large wireline fires in the northwest and west, flying out of Boise, Idaho, and looking at smaller agricultural burning flying out of Salina, Kansas. We did that in the summer of 2019, and with a mix of in situ and remote sensing payloads, and could really look at the way fires looked from space and from the air, and then when actually flying through the plumes. We also had a component that we used flying out of California to function as a virtual satellite. So this shows some sense of what one would see, and then you could actually look down with a LiDAR and see where the particulates were. And then flying through, one can measure the carbon monoxide and see how much pollution there was and get a sense of what the burning was. So it's a combination of looking down and flying through. Another campaign that we did last year also was CAMPEX for Cloud Aerosol and Monsoon Processes Philippines experiment. We took the B-3 and the Learjet, flew out of the Philippines and some of the over the regions there and the oceans around there. That's an area of the world that had really never had that kind of intensive process-oriented field campaign that was designed synergistically with the aircraft and satellites. There's partnered with the Naval Research Lab and the Manila Observatory, so there's a ship on the ground and a lot of surface-based observations to really understand what's happening in that part of the world where you've got a lot of evaporation, you've got pollution, you've got a lot of sunlight. It's a very active period of time, and to really understand especially the interactions between clouds and aerosols and monsoon phenomena circulation. And so in one case, there was a massive smoke plume over Borneo that was observed. It's one of the largest biomass burning ejection events seen. And while a lot of the aerosol mass was near the boundary layer, in some cases, it could get really high up, and you could see it coming out of the clouds. And we've also done some smaller campaigns that were smaller in scale, using smaller planes, and trying to combine with surface-based observations. So we've done a couple in the Mid-Atlantic region. We did one in the Chicago region, one in the New York region, and with a student airborne research program in 2017, we were able to get some information in the West Coast area. I'll come back to saying something about SARP, the Student Airborne Research Program. So these are smaller campaigns, again, using smaller planes than the ones that I talked about earlier. And you can see that some of the things one would do is do repeated airborne mapping throughout the day and to create a proxy data for future geostationary air quality satellites. I know that the TEMPO will be the one over the US. Trying to do policy-relevant research to help state, regional, and federal air quality organizations understand some uncertainties in their emission estimates, and develop strategies for validation of new satellite air quality data products. There's also some particular phenomena that one would look at, especially where you had water and land, to understand the relative concentrations of ozone and precursors over land and over water in the context of the circulations that connect them. And is a joint effort of our research and our applied sciences program. They hope to be working back in the Houston area this coming summer in support of a mission that's being led by the Department of Energy. Now, looking ahead, there's a couple of significant campaigns that we're looking at. We're looking to use the ER2 in a campaign that's abbreviated as DCOTS. It's Dynamics and Chemistry of the Summer Stratosphere. This is also part of our Earth Venture Suborbital program. This one will fly out of Salina, Kansas, and do multiple deployments at different times. And the idea is that especially in the summer, when you have a lot of convection that's lofting water vapor into the lower stratosphere, there's the opportunity as the water vapor gets dissociated, creates free radicals to lead to active atmospheric chemistry, and there's a question whether or not there could be enhanced catalytic destruction of ozone in that region. And because the payload here has a lot of sensors for a variety of species, including free radicals that would be involved in the catalysis, as well as ozone and reservoir gases and dynamical tracers, it's a good way to get information about that. The principal investigator there is Ken Bowman at Texas A&M University. A lot of the instruments are from Harvard and coming from a variety of other organizations as well. And finally, the ACLIP campaign that we're looking to do with the National Science Foundation next summer in Japan. ACLIP stands for Asian Summer Monsoon Chemical and Climate Impact. NSF would bring the G5 from National Center for Atmospheric Research. We would bring the WB-57, which is it's got a pilot and one instrument operator on it, but it's a aircraft that it can't go as high as the ER2, but it can bring a very a large payload, and it's very good for sort of investigating the tropical tropopause region. So, and you can see it's really looking at transport pathways for the Asian summer monsoon and how air connects the upper troposphere and lower stratosphere, the chemical content of air that is processed in the monsoon for ozone chemistry, short-lived climate forces, information on aerosols and what the aerosols do, and water vapor. So that's due for next summer. So if you would like to find ways to get involved in the airborne program, obviously being affiliated with any of the research programs involved can give you opportunities. But there's another way. And that's every year we do the Student Airborne Research Program. We do a solicitation opening up for applications, and we pick students. This year, of course, is different because we had to do a virtual SARP, which did not get the students on the airplanes the way they normally do. But for 11 years, we'd have about 30 students a year from universities around the country, most of whom were rising seniors, and they would get the opportunity to fly on an aircraft and go out in the field and do surface calibration and validation, listen to lectures from NASA scientists, work with research faculty and graduate students. Since we've been doing this for 11 years, there's sort of a longitudinal data set, so students can not only look at the data that they acquired, but they can look at it in the context of data from their predecessors. And since each summer may be different, the meteorological conditions, the chemical conditions may be a little different. So you learn something by comparing the data from one year to the next. So it's been a very highly successful program. The students thoroughly enjoy it. Amazingly large fraction of the students have gone on to do other things, sort of staying in the Earth system science or related NASA science community. And if you're interested in that, we'd encourage you to look for next year's call and apply for that. So with that, thank you very much. If you have any questions, feel free to reach out to us, and we will try to respond to them. Thank you for your attention.